Local maximums and minimums. There are a lot of definitions and theorems in this video, so I don't want to dwell on just reading definitions and theorems. So I recommend that maybe you stop the video and copy these down and think about these things a little bit. But just in brief, we say that a function has a local max at a point if the function value at that point is bigger than all other points. Well, that makes sense. That's all this is saying here. And then the function has a min at AB if the function value at that point is less than all other function values. Now, we say all other function values, we're talking about what we call an open disk around AB. So in a single variable, it's an open interval. In multivariable with two variable input, it's an open disk. So there are a lot of similarities between single variable and multivariable calculus that we'll mention. But a theorem here. So if a function has a local max or min at a point, and both of the partial derivatives exist at that point, then both of the partial derivatives must equal 0. So we're going to be using this when we do some problems. But the idea is this. When we want to find a local max or min, both partial derivatives must be simultaneously 0. And of course, this point, if true, is called a critical point. So let's find a critical point of a function f of xy equals negative x squared plus 4x minus y squared minus 10y plus 7. And we're going to find our partial derivative. Sometimes I put fx of xy, sometimes I just write the notation like this, but it's always at x comma y. So the partial derivative with respect to x is negative 2x plus 4, and I set that equal to 0, and this is true when x equals 2. That doesn't mean that there's a critical point for every single time x equals 2, because we need to find the partial with respect to y as well, which is negative 2y minus 10. And if I set that equal to 0, we get that y equals negative 5. So both of these must be true to have a critical point, which means there is only one critical point, and that occurs at the point 2, negative 5. Now, I have not talked about whether this is a max or min. All I want to do is find the critical point here. Because finding maxes and mins, local maxes and mins, is a little bit more complicated in multivariable than it is in single variable. In fact, quite a bit more complicated perhaps. So there is a second derivative test for local extrema that we use in multivariable. So technicality, suppose that the second partial derivatives of f are continuous on a disk with center AB, and suppose that we have a critical point, that is the partial derivatives, the first partial derivatives at that point equals 0. We're going to find a value big D, which is D at AB. And it's going to be defined as the second partial fxx times the second partial fyy minus f of xy squared. And just a quick note, when the second partials are continuous, then f of xy equals f of yx. So it's really f of xy times f of yx, but we simply put back here f of xy squared. Okay, so this is how we define D. Now we have certain other conditions we have to look at. Suppose that D is a positive value, but also the second partial fxx is also positive. In this case, f has a local minimum. Now, what if D is positive but f(xx) is negative, then f has a local minimum there. And I'm going to tie this back to single variable in just a bit. But we have something else that occurs in multivariable that we don't have in single, which is the following. What if this d value is negative? Then f does not have either a max or a min there, but instead has something called a saddle point. So let's take a look at some pictures, because I want to understand this at least a little bit, try to get some intuition going. And I'm going to start over here on the left side with a single variable type picture. And recall that the second derivative test says if f prime is 0 at a point and f double prime is negative, right, the function is concave down, there's clearly a local maximum there. Now if the graph is momentarily horizontal, that is if f prime equals 0 at a point, and the function is concave up, that is if f double prime is positive, then at that point there's a local min. So that corresponds to parts A and B here. That is, it really corresponds to, I have my first derivatives are 0, and then my second derivative is either positive or negative. And notice there's a lot of similarity there. But let's look at this again. This d, as we defined it, f of xx times f of yy minus f of xy squared. So here's the way I think about this. F of xx is talking about how the function changes strictly in the x direction, or how it's trying to change. I know it's the change of the rate of change, but I think of this as how the function really wants to change and bend in the x direction, like strictly x direction. And of course, f of yy is telling me how my function wants to bend in strictly the y direction. And so you put those together, it's how my graph is trying to bend in the normal directions, if you would, coming into the x, into the y. Now, this back part is talk about how the graph wants to bend in the xy direction kind of simultaneously. So kind of x and y at the same time. That's the way I think about it. So how does it give me pictures? Well, if d is positive, that means this first part is greater than the second part. By the first part, I mean all of this. The fxx times fyy. How the graph wants to bend strictly in the x and the y directions kind of on their own. I would say sort of as they normally do. Now, if d is negative, that means this part is bigger. That has a bigger value. Which means if d is negative, the graph is trying to bend in the x, y directions, both of them at the same time. So when d is positive, I get just kind of a normal graph, maybe parabola in both directions. But when d is negative, I get something like this, where the graph wants to bend in the x and the y directions simultaneously. So maybe x is this way, so I'm kind of bending over on itself, but over here, this would be the y direction, it's trying to bend in the opposite direction. And so if you have a critical point when the function is doing that, you get what is called a saddle point. Because it makes the graph look sort of like a saddle, if you've ever seen saddles on horses. All right, there's the intuition, at least the way I think about it. Let's do a problem or two. So consider f of xy equals y squared minus x squared. Let's find the critical points and determine if they are local maxes, local mins, or saddle points. So we need to start by finding our first partials. So fx is negative 2x, and this equals 0 when x equals 0. The first partial with respect to y is 2y, and that equals 0 when y equals 0. So we have our critical point at 0, 0. This is the only place where we could have a local max min or saddle point. But now we need to look at our second partials. So let's do fxx. So partial with respect to x, then x again, that gives us negative 2. Then we'll do f of xy. So x first, then y equals 0. And of course, that'll be the same as f of yx. And then we want to do f with respect to y, then y again, and that's going to equal 2. So d being f of xx times f of yy minus f of yx or xy, doesn't matter, squared, equals negative 4 minus 0, which is negative. And since d is negative, 0, 0 must be a saddle point. Now, one quick note, because I didn't put it earlier, but what happens if d equals 0? Well, if d equals 0, we don't know what's going on. That's why I left it off. Let's look at a more complicated example, but the same idea. Find the critical points. Are they local maxes, local mins, or neither? We'll start by finding our first partials. So we get partial with respect to x is 4x cubed minus 4y. And this will equal 0 when y equals x cubed. Now let's find the partial with respect to y, which is going to be 4y cubed minus 4x. And this will equal 0 when x equals y cubed. Now, which y equals x cubed and which x equals y cubed works? Because it's not all of them. So how can we do this? Well, let's take our f of y. Let's just look at this one back here. Actually, yeah, we'll do it. This one back here. I'm going to look at f of y again. But what I'm going to do is I'm going to plug this, because this has to be true in both equations. I'm going to plug this one into f of y. So I'm going to get 4 times y cubed, that is x cubed, cubed, minus 4x equals 0. I don't really need the 4's. I'll get rid of those. So we have x to the 9th minus x is going to equal 0. But let's just factor out that x first. So we have x times x to the 8th minus 1 equals 0. And if we do a little bit of work, we see that x equals 0, or 1, or negative 1. Now, we got x equals 0, 1, negative 1. We can now find the y's that correspond by using this here. So correspondingly, we get y equals 0 when x equals 0, y equals 1 when x equals 1, and y equals negative 1 when x equals negative 1. So we have 3 critical points, 0, 0, 1, 1, and negative 1, negative 1. So we need to check each of these individually. Let's get our second partials, fxx, which is going to be 12x squared. We'll get our mixed partial fx then y, which is going to be negative 4, which is going to be the same as the other mixed partial. And then fyy is going to be 12y squared, which gives us d is going to be 144 x squared y squared minus 16. So for the first example, we didn't have any x's or y's left over, so we didn't need to do any extra work, but here we need to do a little bit more work. And we're going to plug in each of these points. So let's find d at 0, 0. That is when x, y equals 0, 0. This gives us negative 16. So I know that we have a saddle point because d is negative. Let's try d at 1, 1. That's going to give us 144 minus 16, which is positive. So we need to do a little bit more work. We need to find fxx at that same point, which is going to be 12. I don't even need the y value, but I put it there anyways, which is also positive. So the combination of these two tells us this will be a local minimum. And finally, d at negative 1, negative 1. If we plug that in, we get 144 minus 16 again, which is positive. So we need to do more work and find f of xx at negative 1, negative 1. Again, the y is not necessary. And this once again gives us 12, which is positive. So again, at negative 1, 1, there will be a local minimum.